Yeah, you need to pass tests. You're right. Okay, let's talk about Bronsted-Lowry. Because that's his name. This guy's Danish. No, not German. He's Danish. And so it's not really an O. It's whatever letter that is in the Danish language. Okay. Lowry's British, and they basically came up with the same acid-base theory at about the same time. So they're both given credit for it. Now I forget which one was which. One of them submitted. One of them submitted a paper for publication. I think it was Bronsted. I'm not sure of that. And it took a little while for it to get published. In the meantime, the other one, and I think this was Lowry, presented basically the same thing at a conference. So basically they both published at the same time. They're both given credit for it. Does that make sense? No? Okay. All right. Now, why should we have another acid-base theory? Because the first one doesn't work all the time. Okay? We know, for example, and this was in the video a minute ago, that ammonia, when you dissolve it in water, it behaves like a base. If it behaves like a base, it is a base. You ever heard the thing, it walks like a duck and talks like a duck?
Duck.
Yeah. Well, that was President Reagan was famous for saying that. If it behaves like a base, it's a base. Okay? Because acids and bases are what they are because of what they do. Okay? Acids and bases are what they are because of what they do. Okay? Well, unfortunately, there's no hydroxide in these formulas to meet the Arrhenius definition of a base. But it behaves like a base. So now we need something else that explains some of these kind of phenomena. There are lots of things that behave like acids and bases that the Arrhenius theory would not predict is an acid and base. In fact, Bronsted-Lowry is limited too. Okay, there are things that behave like acids and bases that don't appear to be acids and bases in either the Arrhenius or Bronsted-Lowry theory. So we need the Lewis theory. I'm only going to tell you about the Lewis theory without going into a lot of detail. Okay, but Bronsted-Lowry, let's talk about what it means, what it says. Now, under Bronsted-Lowry, an acid is anything that donates a proton to something else. Huh? Ooh, that's a good point. Almost the same definition. One happens only in water. Okay? And it says it releases a hydrogen ion in water. It doesn't say the proton goes anywhere. Arrhenius said it only is donated it's only released in the water. So it's like it's sort of floating around there willy-nilly, like somebody on a float on a pool. Just not really doing anything, But Bronsted-Lowry says it's going to something. Big difference there, and we'll talk about why that is in a minute. All right? And then, but while we're here, let's talk about what a base is according to Bronsted-Lowry. A base is anything that accepts that donation. Hey, come on in. Okay, remember what we said about protons? What are protons? Same thing as a hydrogen ion. Okay? That's because a hydrogen atom only has one proton and one electron. In order to become a positively charged ion, it's got to give up its electron. All that's left is a proton. Okay? So let's look at a typical Bronsted-Lowry equation. We looked at that for Arrhenius a minute ago. We looked at some equations for Arrhenius. Now let's look at Bronsted-Lowry and look at how it sort of expands this idea of how an acid and base do what they do. So let's use the same acid, HCl with a little l. Okay. Since an acid is something that donates a proton to something, we have to have something in the equation that it's going to be able to donate that proton to. Alright? Well, let's make that water. So if it's going to donate a proton, we can symbolize that as H+, and it's going to donate it to water. I want you to stop and predict now. What products are we going to get if that happens? Predict what products we're going to get if that happens. Everybody got it? I don't see anybody saying no. Alright. If a hydrogen ion leaves this chlorine over here, or chloride, what are we going to get? What's going to be left? Okay, and it's going to be aqueous because it's actually dissolved in water now. Okay, we got water here, it's going to dissolve. And that hydrogen ion leaves here and it goes and joins up with the water molecule right here. So what is that going to give us? Alright, and if you didn't know, since somebody said it already, this is called hydronium. So since this gave up a hydrogen ion and donated that hydrogen ion to something else, by definition up here, that makes this an acid. And since water accepted that proton, that's going to be our Bronsted-Lowry base. Whatever substance gives up the hydrogen ion, and it becomes more complex than that when you understand the full impact of all of this. But for right now, it's enough to say that whatever is left over after the hydrogen ion leaves to be donated somewhere else, whatever's left over is the conjugate base. Okay, so what's our conjugate base over here? The chloride. Whatever's left over after the hydrogen ion or the proton leaves to be donated to something else, that leftovers, or those leftovers I suppose, is the conjugate base. You got it. Whatever that hydrogen ion got added to, is the conjugate acid. Nicely done. All right. Now, let's see. Let's remind ourselves about our potassium hydroxide. Got potassium hydroxide. We're going to put it in water. we get the potassium ion and the hydroxide ion. Excuse me. All right. What we did when we were looking at the Arrhenius acids was we took the products of the dissociation. This is dissociation when you break it up. And this is, even though it doesn't quite look like quite the same thing, this is breaking it up using Bronsted-Lowry. Okay? It's a little bit different because we end up forming sort of something other than the immediate breakup product. Okay? But this is the dissociation equation for Bronsted-Lowry. All right? And this is just a dissociation equation, straightforward. All right? It happens to fit Arrhenius. What we did before was to take the products of both of the dissociation equations, put them together on the left-hand side of an equation to write a neutralization equation. Okay? I want you to do the same thing now. Okay? I want you to take the products of this dissociation here and the products of this dissociation. Both of those become then the reactants for a neutralization equation, and I want you to write the products of that neutralization equation. Okay, Heather, what products do I write? Huh? Cl negative. Okay. And? K plus. H4. You ever heard of that before? H4 too? Oh, would that make more sense? How about that? Looks a lot like the Arrhenius equation, doesn't it? Right? Here's our Arrhenius equation here. Right here. And in this case, we're getting 2 waters instead of just 1. Okay? Other than that, it's pretty much the same, right? Yes or no? Yep. Write the net ionic equation now. This is the complete ionic equation. And I want you to write the net ionic equation now. So let's see. Is that what you guys got for the net ionic equation right there? Okay. How did we get that? What actually happened to all the stuff here to make that happen? What disappeared? Huh? Okay, I'm really not looking for what happens between here and here. You're right. The chlorine and potassium are the spectator ions. They're just sitting in the stands or on the bench. They're bench warmers maybe. Okay, they're not really doing anything. Okay? But right here, how does this react with that to make that? What happens between here and here to have that happen? What? It does neutralize. Look up here. Not just the H, but the H plus, the proton, right? Goes right there. Well, what does that make this? But I mean, what does it make? It does make it our acid, right? Because it donated a proton, doesn't it? Huh? And this is our base. Well, where's the conjugate acid?
The conjugate acid is one of the waters, and the conjugate base is the other water.
Very well done. Okay, so we got two waters here. One day you're awake. Okay. All right. So one of these has to be the conjugate acid. Whichever hydrogen, whichever water molecule started out as hydronium and the proton left, that's the conjugate base. And whichever hot water resulted from the proton joining up with it is the conjugate acid. Yep, conjugate base, conjugate acid. Okay, it accepts a proton. Wait a minute. Accepts a. No, this is the this one becomes the conjugate
acid.
Yeah, it does. That's true. Seems kind of strange that way, but it does. You're right. Okay. Had to stop and think. So I'm not awake today. You are. There you go. Okay. Look at here. Water is both an acid and a base, and in the same equation. Whoa. And that's the power of the Bronsted-Lowry theory. It allows you to treat water like it's an acid and a base because it behaves that way. Where Arrhenius doesn't give us that power. According to Arrhenius, it's kind of, you can get it, but it's kind of hard to see how you get it. Okay? A little more complete understanding of acids and bases. Any questions about Bronsted-Lowry theory? For right now, anyway. No. We've got another lab to do, and we've got to learn to do acid-base stoichiometry. And some more about You got to do let's see, neutralization curves. Yeah, a lot of things to do. Okay. All right.
So you said we're on the downhill part.
What now?
So you said we're on the downhill part where it gets easy.
Well, after you learn how to do stoichiometry, everything else is applying this stuff. All this stuff is not really new theory. We're just applying all this stuff now in different ways.
Mystery never ends.
That's right. It never ends. Science is like that. It never ends.
Stuff you don't like, stuff that keeps going, don't keep going.
Everything keeps going when you think about it. Everything does. What?
Not really.
Like what?
Good.
Yeah, but our understanding of dinosaurs keeps going.
English, yeah.
English doesn't keep going?
Not really. English will constantly forever keep going.
Yeah, people keep doing new stuff with English.
English, and you know English doesn't read it, and you're done.
Well, we know math.
You're not learning it.
Ask your English teacher if the English language is a dynamic or a dead language.
It is dynamic.
Thank you. Okay. Remember in Unit 2 when we figured out how to do those electron dot formulas and sharing arrangements to put together hydrogen and oxygen to make water? Do that for me. Just remind yourself. How do you put together hydrogen atoms using a Lewis dot or electron dot formula and water to make a Lewis formula, a Lewis dot formula for water? Can you do that? You remember that? See if you can do that. Electron dot formulas for hydrogen and oxygen, and then go through the sharing arrangement to create a Lewis dot formula for water. Now, I've warned you this stuff was going to come back again. You know? A Lewis dot formula for water. I want you to show me how you get there. You starting out with just the electron dot formula. Well, what's the electron dot formula for hydrogen? 1 dot. What's the electron dot formula for... Don't tell me out loud. Just think about it. Look on your periodic table. You're doing the electron dot formulas for water and oxygen. For hydrogen and oxygen. Then you're doing the sharing arrangement. Then you're writing the Lewis dot formula for water. And the guy who came up with these dots things, he's also the guy who came up with a third definition for acids and bases.
Why didn't you come up with something?
I come up with all kinds of stuff.
Why didn't you get it published?
Huh? I'm not as smart as Lewis or Bronsted-Lowry or Arrhenius.
You don't know your potential yet.
They may not have been smart. They could have just been really stupid.
If they could have been cuckoo and we just are following some
Cuckoo for Cocoa Puffs.
idiot theory.
And let's see now, the black part here of this drawing is the electron dot formulas. The red part, the bubbles here I've made around, or circles I've made around these dots, that's our sharing arrangement. And from this then, we can get, well, I'm not really doing very good with this arrow today. We can get the Lewis dot formula for water. Okay? Let's look up here at hydronium. Hydronium came from, and if we kind of remember what we did with Arrhenius, it all started out with just hydrogen ions here. Okay? So the hydrogen ion joins up with the water. So if this is our water, and a hydrogen ion joined up with that to make the hydronium, show me how to make a Lewis dot formula, same thought process, for hydronium. Show me the process for creating, putting those together to make hydronium. Huh? Sure it does. there's not really a sharing arrangement exactly. How many electrons does a hydrogen want to be as stable as can be? No, that'd be neutral charge if we have one electron. To be as stable as can be, it wants 2 electrons. Huh?
It'll still share one, but it'll leave a positive charge.
There you go. Sometimes you just got to put it down on paper and look at it.
Things aren't always happy, Rebecca. From life.
This hydrogen ion doesn't like being without any electrons. Okay? How many electrons does it want? 2. Can it get 2 electrons if it shares any with water? Huh? Can it share any electrons with water? Yeah. Got 2 sets of electrons it can share with. Huh?
You're very particular about your drawings.
I know. So students tend to be confused if I'm not very particular. Not really. I'm not worried about it, but I try to make it as clear as I can to the students I'm teaching, trying to teach. Okay? All right, now, this has a neutral charge. The water has a neutral charge. The hydrogen ion has a positive charge. You can't just get rid of the positive charge. So when this joined up with that, it still is going to have a neutral plus positive gives you positive, like 0 plus 1 is still 1, right? So this has a positive charge. I'm going to put a bracket around it because I want to show that that positive charge is shared over that entire structure and not just a positive charge on a single atom or something, okay?
So the hydrogen just makes the whole thing positive.
Sure, it brought the positive charge over here. It's split it positive, right? Does that make sense? This is kind of the segue idea between Bronsted-Lowry and the Lewis theory of acids and bases. So the next video on the Lewis theory.